Thank you very much. Today I will talk about the hybrid orbital theory. Though it is really hard to describe hybrid orbital theory by using only 10 minutes, I will try my best to describe it. But when I will get enough opportunity in future to show you the real classroom environment, I will use the active learning cycles and the evidence-based teaching practices in the real classroom to show you how I normally teach. Um, so now let's talk about what is the learning objective. So today, after finishing this teaching demonstration, you will be able to understand what is hybridization and what is hybrid orbital theory. And then we will talk about why hybridization is important. Then you will be able to understand at the end of this session to differentiate between SP, SP2, and SP3 hybridization with some explanation, bonding behavior to explain some compounds. Okay, now before going to the real hybrid orbital theory, let's review valence bond theory, which is important. So, what is valence bond theory? Valence bond theory is a chemical bonding theory which was proposed by Hitler and London to explain the covalent bond quantitatively by using the quantum mechanics. And in valence bond theory, it explained the bonding between two atoms through the overlap of half-filled atomic orbital theory. Very important. It explains the bonding between two atoms by using the overlapping of half-filled, very important, half-filled atomic orbital. See, atomic, not hybrid orbital. This is really important to understand. And uh, we can explain the hydrogen molecule by using the valence bond theory. So one hydrogen atom, another hydrogen atom to form the H2 molecule. So I believe you know the electronic configuration of hydrogen, which has one electron, which is the simplest atom in this world. 1s1. So s orbital is circular. So if we represent this 1s orbital with one electron, and then another hydrogen atom with another electron in the s orbital, if we combine these two hydrogen together, then what happens? Then these two atomic orbital, half-filled atomic orbital combine to form the S2 molecule. So this can be explained very nicely by using valence bond theory, by using the half-filled atomic orbital. But we cannot explain the bonding behavior in methane, ammonia, and ethane by using the valence bond theory. So then um, to explain this phenomenon very nicely, Linus Pauling improved this theory by introducing the concept of hybridization, which is called the hybrid valence bond theory. So today we will, by hybrid orbital model, we can explain thousands of molecule consisting carbon, nitrogen, and oxygen atom with a hydrogen. So you know that there are a plethora of molecules that can be formed by using permutation combination, carbon, nitrogen, oxygen, and hydrogen. So by using the hybrid orbital theory, we can explain a large, so many molecules to explain the three-dimensional arrangement in space. So what is hybridization? So hybridization actually the mixing of two things to get a new things. So for example, if we mix a horse and donkey together, we will get them new. So now here is very nice definition of the hybridization. Hybridization is the intermixing of two or more pure atomic orbitals of an atom with almost the same energy to give the same number of identical and degenerate new types of orbital is known as hybridization. And the orbital that is formed is called the hybrid orbital. It is really important to see this definition. I use the different color code over here. Pure atomic orbitals, mixing pure atomic orbitals, how many? Two or more of an atom whose energy almost the same but not same. After mixing, we will get the same number of orbital that we initially use to get identical, meaning similar shape, and degenerate, meaning same energy level orbital. We will describe this later. So now, here are an example. Here are the some different types of hybridization that is possible. So sp meaning one s and one p, total two orbital. Now sp2 is two p orbital and one s orbital combined to get three sp2 orbital. Similarly, sp3 one s three p and sp2d, 1d orbital, 2p orbital, and 1s orbital, total 4 orbital. So now, today, we will talk about only sp2 and sp3 hybridization. Before going to that orbital, let's see how atomic orbital look like. So today we will talk about only s orbital and p orbital. The shape of s orbital is circular and p orbital is dumbbell shape. But there are three p orbital: px, py, and pg orbital. If we combine together, we will get this combined orbital, which are perpendicular to each other, meaning 90-degree with all of these px, py, and pg orbital. Now, let's see. What is sp3 hybridization? sp3 hybridization when we mix one s orbital and three p orbital together to get four orbital mixing, and total getting four orbital sp3 equal identical and equal energetic sp3 orbital. Now here is the three-dimensional structure, molecular geometry of the sp3 hybridization molecules, that is tetrahedral shape, and the bond angle between the orbitals should be 109.5, and this is called the hybrid orbital. Similarly, sp2, 1s, 2p, and 1p orbital will be unhybridized, so we will get three hybrid orbital. The shape should be trigonal planar, and the bond in between this hybrid orbital will be 120-degree, and this is an hybrid orbital which is perpendicular to this hybrid orbital. Now, sp orbital is pre-hybridization. One is 1p and two remaining will be unhybridized. This should be linear. Bond angle will be 180-degree, and two unhybrid orbital will be remaining. Now let's discuss about methane molecule. To explain the sp3 hybridization in methane molecule. Here is carbon atom is the center atom. The valence, the electronic configuration 1s2 2s2 2p2, and this is the valence electron 2s2 and 2p2, and their energy 2p orbital is little bit higher energy compared to the 2s. And here is when we excite this molecule, then this the one electron will move into the empty orbital. Now if we mix together, then we will get the average energy in between these 2p and 2s for identical hybrid orbital. Now, if we get this tetrahedral hybrid one carbon atom, and then if we add then another four carbon atom combined with this to form the sp3 CH4 molecule, and this is the sigma bond, and the bond angle will be 109.5. Thus, we can explain the, all of the bond angle in many compounds very nicely. Now, let's talk about um, sp hybridization due to time constraint. So here we have two carbon, and this is sp. So one s and one p orbital combined, two unhybridized orbital will be remaining. Now their shape will be like linear and two unhybridized orbital. If we take these two carbon, one hydrogen overlap with here, another hydrogen over here, and this two hybrid orbital will overlap with each other to get the sigma bond. Now here is the px orbital, px, py. So these two unhybridized orbital will overlap, side by side overlap to form two pi bond, one pi bond, another pi bond, one is sigma bond. Now we can explain in many molecules by using the hybridization. This is we can here are some example that we can explain all these molecules by using by this hybridization. Thank you very much, and we will learn more